welcome to today's lesson. Today we're going to look at the concept of being mutually exclusive, as well as some other concepts later on, and we're going to be using Venn diagrams to help us better understand these concepts. Now, if you haven't seen a Venn diagram before, let me just start off with this rectangle. And if we were looking at some kind of an experiment and said, well, in this experiment we have certain events, and we might designate that as A, then I would draw that something like this. This would be representing those events, those particular outcomes. And everything outside of that little circle is the complement of this event. Okay? So if you had, for example, rolling a dice, and maybe event A was rolling a 1. So you'd have the 1 would be considered event A, and the complement would be 2, 3, 4, 5, and 6. You'll notice that when you add the probabilities of A and its complement, you do get 1, or 100%. Now let's look at a more complicated Venn diagram, and that will help us understand the idea of being mutually exclusive. When we talk about things being mutually exclusive, we're talking about two separate events. So, for example, we might have one that we designate A, and the other will designate B. And what makes them mutually exclusive is that they have no outcomes that are in common. Now, what you've got to picture is something like we do one experiment, and maybe that experiment is rolling a die. Perhaps event A is rolling a 2, and event B is rolling a 4. Well, there's no way, remember this is one experiment, we're doing it once, there's no way you can get a 2 and a 4. Okay, there's nothing that's shared there, there's no overlap. So this would be a very simple example of two events that are mutually exclusive. They have no shared outcomes. Now, there are ones that are going to have some overlap, and we're going to be looking at an example of that in a bit here. But I'd like to look at some general rules here about probabilities before we get into that example. I'm just going to keep this very general, and these will be coming back later on as we look at other things. But suppose we had our Venn diagram depicting event A and event B. Okay. Now this part here, this part that's overlap, is referred to as the intersection of these two events. Okay. These are shared outcomes. And you can see these are not mutually exclusive. They have some outcomes that are shared, and that's what this little overlap section depicts. That little section that's shared, the one that I've shaded, is written as A intersect B. Okay, so that's kind of this little notation is saying that's the part that is, if we want to use English words, that's the part that is A and B. Okay, and they use this little upside down symbol to represent the word and. Another way to think of these Venn diagrams, something we might be interested in later on as well, isn't just the intersection part, but it might be, again we have some overlap here, so we have set A and set B. We might be interested in all of this stuff, that is everything that I'm now shading. Okay. And the way we would think of that in English, maybe it's easier to start with the English, is to think of that as A or B. Whatever these outcomes are part of A or B. Now, the important thing there is we also have a little symbol, and it looks like this, A with a U, and in this case it kind of means the union of A and B, so it's very much sort of makes sense to have a U there, so A union B. We also have a little formula that's helpful to us. Now, I'm keeping this very simple, and it does work, of course, when we get to probability as well. But the idea is that we take all the elements of set A, so it's kind of like saying, well, everything within this circle here. Okay. So we have all of A plus all of B, which is all of this stuff here. Now, you'll notice something happens here. If I sort of use a cross shading to indicate all of A, there's all of A. Okay. And then I say, oh, and I want to include all of B. So we take all of B here. Something's happened here, and that is this little intersection part gets doubled. Okay, because it's already part of A, and then when we add all of B, we're including this part again, even though it was already there. So what we have to do to fix this up to get A or B, or A union B, is we take set A plus set B minus that intersection. So that would be minus A intersect B. And by taking one of those intersections out, then we get basically all of this part here, as well as all of this stuff over here. And that's what we want, of course, when we say the union of A and B. Or I guess we be careful, the union of A or B. All right, let me look at some examples that really involve some specific numbers and how we're going to use Venn diagrams to do pretty much a very common sense kind of an approach. And so let's see here. Let's say we went around the school and we were doing a bit of a survey, and we came up with some information about math, physics, and chemistry. So what we have is a situation where we've surveyed students, and we have percentages or probabilities of students who take math, students who take physics, students who take chemistry, and students who take perhaps math and physics. They take both. Students who take maybe all three, and so on and so forth. So here's kind of the results of our survey, and I'm going to give these as percentages, although it would be just as easy to think of them as probabilities. Okay? So let's start off with those students who take all three. What percentage of students did we find that take all three of these? We found 5%. And then we have some more information. Some who take math and physics. And math and physics, we have 20% students. Then we take math and chem. We'll just keep the first letters, makes it a little bit simpler. Math and chem, we find only 10% of students who took math and chem. And then we have physics and chemistry. And what percentage of students? That was 15%. So that's what we got from our survey. Now we're going to take a Venn diagram and construct it based on these three courses and the information provided, and maybe fill in some of the gaps. So this is now going to represent the situation here. And this time we have three things on the go. So I'm going to draw three circles. And since all three of them are taken by 5% of students, I'm going to overlap all three circles. It'll look something like this. If I draw this big enough here. I get the feeling that's not going to be quite big enough. Let me just redraw that slightly bigger. I think it'll be easier on your eyes, and we certainly don't want to strain you there. So what I'm going to do is just take a whole bunch of this section here and draw it sort of like this. There we go. That should be a lot better. Okay, so let's make this the math set. We'll make this the physics set. We'll make this bottom one chem. Okay, if we start filling in the information, well, all three would be this little part that's right in the middle. That's common to all three circles. Okay, that's the intersection of the three courses. That's 5%. Now, if you wanted to work with probability, and all you would do is take 5% and think of it, instead of 5%, think of it as 5/100ths or 0.05. In other words, it's really the same thing, but it saves us having to write the little percent symbol. So I'm going to write it as a decimal, and in that way it kind of converts it already to a probability. And all it means is that if we randomly selected a student, the probability that that student is taking math, physics, and chemistry is 0.05, or 5%. Let's take some of the other information now. So we've taken that one and we've processed it. What about math and physics? Well, math and physics is this little intersection right in the middle here. We know that's 20%, or 0.2. Now we already have 0.05, so what I need is 0.15. Grand total, 0.2. So that's that one. Math and chemistry. Well, math and chemistry is this intersection here. We already have 0.05, and what we want is 10, or 0.1. So I need another 0.05. Done. Physics and chem. Physics and chem is going to be the intersection over here. And again, we've got our 0.05. We need 0.15, so I need a 0.1, or sometimes it's nice to keep two decimals all the way across, a little easier on sort of visualizing the math, and maybe less likely to make any sloppy mental errors here. Okay, now that's pretty good, but in order to continue, there would have to be more information provided, because we've got all this here, but somewhere along the lines in our survey, hopefully we've got more information so we can fill in things like what percentage of students or probability of students are only taking math. Now, in our survey, I didn't write these up yet. Actually, I'll just take advantage of these written right here. Math, pure math, or sorry, not pure math. Any students taking math, the total students taking math, 55%. Now what that means, and that's why I had to catch myself here when I said pure math, math means this entire circle. That means some students, they're taking physics, some are taking chemistry as well, and they're all taking math. So this entire circle should represent 0.55. Okay, so what do we have in this circle? Well, we have 0.05, 0.05, and 0.15. So that means we already have here 20, 25, and to get 0.55 we need 30% more, or 0.30. Now this is really important, filling in these little spaces like this, because ultimately when we start asking some of the questions, having it already filled in your Venn diagram makes it so easy to just glance at it and identify what's what. Physics in our survey turns out 45% of students surveyed are taking physics. So what do we have in the physics circle? Well, we have 15, and 5 is 20, 30, we want to get to 45, so 0.15. And then down here in chemistry, it turns out only 30% of students surveyed are taking chemistry. And what do we have here? 5, 10, 20, so we need another 10% there. Now, just when you think, oh, I filled it all in, there's one more thing you have to do. Remember, this whole thing represents 100%, or a probability of 1. So what we can do is we can take the number of students surveyed that don't take any of these courses and answer that question. So in other words, what you do is say, well, what we have represented here is 30 and 15, that's 45, and another 15 is 60, 70, 80, and 10 is 90. So there's 10% of them that take none of these courses. So we're going to put that outside here. Okay? And sometimes that's a very important thing that students will overlook. So now that we filled out our Venn diagram based on all of this information, let's look at some of the questions that we can answer that I think you'll find are pretty straightforward now that we've got our Venn diagram totally filled in. Okay. And by the way, just so you get the idea of the terminology, none of these courses are mutually exclusive. All of these events have overlap. Okay, so none of them are mutually exclusive. Some questions might be things like this. What probability of students, or what is the probability that a student is taking math? Well, that means this entire circle, and that was kind of given information from the survey. But in any case, what do we have here? We have 30, 40, 55. So a probability of 0.55. So if you randomly selected a student in the hallway, the probability they're taking a math course is 0.55. What about something like, say you had the probability they're taking physics, but not chemistry. Okay, so physics, but not chemistry. So here we have physics, and there's an overlap with chemistry, but we don't want any students who are taking chemistry. Well, it's pretty easy to see. We've got these guys here, 0.15, and these guys here that are taking math. But notice they're not in with chem. So we have 0.15, 0.15, so we have 0.30. Okay. Let's look at something like a probability of a student not taking physics. Well, again, we're just going to randomly pick a student in the hallway. What's the probability that student is not taking physics? All right, what we want is everything that is outside of this circle. Now you have to be careful. We've got 30, 40, 45, but also this. So 55. Okay. Often it's easy to forget about these guys over here, but they're not taking physics. They're also not taking math or chemistry, but that's beside the point. Let's look at a couple more here to make sure we've got all of the Venn diagram stuff. The probability of neither math or chemistry or physics. Well, that means none of this stuff that's in the circle area here. So we already worked that one out quite easy. 0.1 or 0.10. Just to see a couple of these ones with the notation. How about a probability of math? And if we throw in the word, say math and physics. Okay, and so this is looking for the intersection between math and physics. Now it seems to me that was given information, but nevertheless, just so we're familiar with this little notation, math and physics would be just this little intersection of the 15 and the 5, so that's a 0.2. Okay, probability of 0.2. And we'll just do one more here. Just got enough room to squeeze that in. How about, say, math union physics? Okay, and this would be translated as math or physics. Sometimes it's just easier to look at your Venn diagram and count them. Math or physics, and this is the last one so I can muck up the diagram here. Math or physics means this stuff. Everything is contained within here. Okay? And you could use our little formula that said you do all of the math plus all of the physics, and then you subtract the intersection because it would have been duplicated. But it's just as easy sometimes when you have your Venn diagram is to just add these ones that are contained within that little boundary. Just add them up. 30, 35, 40, 55, 65, 70, 80. So it looks like 80%, or probability 0.80. Okay, that's the idea of the Venn diagram, and it can be very, very helpful to us, especially when we're talking about situations with events that are not mutually exclusive. The next thing we're going to look at, and the last thing that we're going to look at today, is another concept that's also very important and will be very important with the material we look at later on. But it's the idea of independence and dependence. And in this case, we're looking at independence versus dependence. Okay, so what's the big idea of that? Often students get confused between mutually exclusive and independence versus dependence. So I'm going to try to make that very clear. With mutually exclusive, we had one experiment, so kind of like at one go of it. Different events, but it's all simultaneously done in one experiment. Can you have any outcomes that are shared? If not, then they're mutually exclusive. Not to be confused with the idea of independence and dependence. And maybe the best way is to show you with a little bit of a description here. Two events, maybe I better write this up. Two events are considered independent. If the probability, actually not the probability, if the occurrence of one, so you'll notice that they're not simultaneous. It's not like you do them both at the same time, it's a single experiment. No. Okay, it's like one followed by the other. Okay, if the occurrence of one doesn't affect the probabilities of the other. So in other words, you do some kind of a little experiment, and whatever happens in that experiment has no effect on the other experiment you're about to do. So a good example of that would be something like this. If you flipped a coin, so you tossed a coin, you're going to get heads or tails, and then you decided afterwards, as part of this, well, I'm going to roll a die, and with a die you get 6 possible outcomes for each one. So possibly if you got heads, then there were 1, 2, 3, 4, 5, or 6. Or if you tossed tails, you could also get 1, 2, 3, 4, 5, 6. Okay. Now, whether the coin lands heads or whether the coin lands tails, these probabilities are unaffected. Okay. It makes no difference to rolling the die whether it was heads or whether it was tails. And that's the idea of these are independent. Okay, so these two events are going to be independent. Now, an example would be something like the probability of, say, the coin landing heads followed by a 5. Okay, the probability of heads and the probability of 5, those are going to have no effect on each other, and we could just work that out by saying we do have a rule for probabilities like this that kind of flow along in a sequence, and if they're independent, the rule is then you can take the probability of the first and multiply it by the probability of the second. Okay, and that's called the multiplication rule, and that works if they're independent. Okay. Now, to try to make that sort of clear to you, let me just show you an example of some that aren't independent and show you that this multiplication rule, which is kind of like following along the branches and working out your probabilities, that doesn't hold up if they're not independent. So let's just look at a simple example with cards. Cards generally lend themselves quite well to these kinds of independence versus dependence kinds of examples. Let's have a little look here. In this experiment, we're going to try to draw 2 aces from a regular deck of cards. And I'm going to do the tree diagram again and sort of analyze what could happen. Either when you draw the first card, it's going to be an ace, or it's not going to be an ace, right? I mean, that's ultimately what we're looking at here. And if it is an ace, well, you take the next card. And by the way, we're not replacing the card. That's a very important little detail. we draw the first card, look at it, put it aside, and then draw another card from the same deck. On the second draw, we're going to get an ace or not, and same thing happening down here. Ace or not. Now, let's look at some of the probabilities as we mosey down these branches. Probability of getting the ace on that first draw is 4 out of 52. Okay, we have 4 aces out of 52 cards. So not getting the ace is the remaining 48 cards out of 52. When we go to the second draw, however, everything's affected here by what happened in this first experiment. First of all, whatever the case may be, you're certainly going to have only 51 cards. Okay. So everything's out of 51 now because we took a card out of the deck. If that card was an ace, well, by golly, there's only 3 of them left. So 3 out of 51 probability. If it was an ace, not getting the ace, well, there's still 48 cards in the deck remaining that are not aces. But if it's not an ace, the probability now, well, there's still 4 aces in the deck. And not being an ace followed by not being an ace means we only have 47 cards left. Now, if you look at this thing, when they are independent, okay, the rule says the probability of, and we could call each experiment here, let's see, I'll use A and B. A and B, and if you A and B occurring, I won't bother with the little notation, but A and B occurring is the upside down. Oh, what the heck, I'll throw it down underneath here. Okay, that's the and notation. So A and B occurring, if it's independent, should be the probability of A times the probability of B. Well, as we can see what's going to happen here, the probability of A being successful would be 4 out of 52, and then the probability of getting an ace the second time, so B being successful, is 3 over 51. So we multiply these two things together. That's the probability of an ace followed by an ace. Okay, but that does not equal, okay, so our actual result, what we know is the probability getting that from our tree diagram, that does not follow this rule here, because the probability of getting an ace is 4 out of 52, and the probability of drawing an ace is 4 out of 52. What's happening here is, of course, when you think of experiment B here, that's just saying, and I guess I should have wrote it up here, but experiment A, I'll try and cram it in here, is you draw an ace from a deck of cards. And experiment B is the same thing. Draw an ace. And so now when we say we want to follow B, or follow A with B, that probability gets altered by whatever happens in A. And so these are not independent. Okay, the one experiment has a dramatic impact on the second one. It should have been 4 out of 52, but it's all getting messed up because of what's happening prior to it. So that's the idea of independence versus dependence. These are dependent. Okay, your probability might get better or worse depending upon what happened before. Hence the name dependence. So that's what we're looking at today, and that's where I'm going to stop for now. That's probably more than enough stuff to absorb. So